Section 2.2, Supervised Learning. We now focus on supervised learning and outline key concepts, practices, and terminology. Supervised learning is about predicting an outcome y hat for y, where the prediction is based on a vector of input features, x. When y is from a finite discrete set, then the task is called classification. And when y is continuous, then the task is called regression. We begin with overviewing basic regression in the context of linear models and feature engineering. We then discuss aspects of binary classification, which is the case when y only attains one of two possibilities. The more general multi-class classification case, in which y takes on multiple possibilities, is presented as part of a specific example in section 2.3. We close this section with a high-level overview of several methods and general approaches to supervised learning. Regression and feature engineering. We begin by considering a very simple univariate example where the scalar p equals 1 feature x is the average number of rooms per dwelling and y is a median value of owner-occupied homes in thousands of dollars. So x is rooms and y is value of a house. These variables, respectively denoted Rm and medv, represent data from the well-known Boston housing dataset. Footnote 2. This dataset originally published has 506 observations, where each observation is associated with a suburb or town in the Boston, Massachusetts area. Of these observations, 16 are capped at Rm equals 50, and we remove these to stay with n equals 490 observations. So we have 490 observations. A regression model y equals f theta of x attempts to predict the median house price as a function of the average number of rooms. To illustrate this concept, consider the well-known simple linear regression model, where f theta of x is beta 0 plus beta 1x, and the parameter vector is theta, which is beta 0 and beta 1. Notice that in this case, the dimension of the parameter vector is d equals 2. This model can also be described statistically via y equals beta 0 plus beta 1x plus epsilon, where epsilon represents the error or noise term as it models the gap between y and f theta of x. In statistical theory and practice, assumptions about the probability distribution of epsilon go a long way as they support inference outputs such as confidence bands, hypothesis tests, and more. However, in practical machine learning culture, one often ignores epsilon and such statistical assumptions. Provided feature data x1 through xn, and that is Rm, the average number of rooms per house in a geographical area, and corresponding label data, that's y1 through yn, that's medv, that's the median house prices in a geographical area. The training process involves finding a suitable or best theta hat, which is beta 0 hat and beta 1 hat. In section 2.3, we study the process for finding theta hat via minimization of a loss function. Yet at this point, let us just consider the model parameters, also known as parameter estimates theta hat, as an outcome of training. Figure 2.3a presents a scatter of the xi-yi pairs. So that's 2.3a above here. The parameters estimated for this model are beta 0, which is about -30, and beta 1, which is about 8.3, both with hats. The figure also includes a plot of the fit or estimated model f sub theta hat as a red line. So you see in A, the red line, I'll highlight it here in red, that's this red line, and that's your estimate. That's a line resulting from beta 0 and beta hat. Clearly, with such a model, any unseen new observation, x star, can be used to make a prediction y hat is f theta hat of x star. If one is willing to make statistical assumptions about the error epsilon and probabilities of error, then an extra benefit of the model is the confidence bands presented as the gray shaded area around the red line. Most of the modeling described in this book uses very complex models that do not take such a statistical approach, and hence built-in confidence outputs such as these confidence bands are often not available. We also mentioned that the estimated parameters in such a model have an interpretation. For example, beta 1 hat equals about 8.3 indicates that increasing the average number of rooms by one room implies an average rise in the median price of about $8.3 thousand. Many types of statistical models have the benefit of interpretable parameters. Yet in the world of machine learning, where models are often very complex, parameter interpretation is an exception rather than the rule. As a follow-up arising from the same data set, consider the relationship between the variable x taken now as the percentage of the population that is of low socioeconomic status. That's L stat. And the variable y, again taken as m med v, that's a median house price. A simpler linear model to fit this will yield parameter estimates theta hat, since in almost any case one can fit any model to data. However, the model may not always be suitable for the data or process at hand. For example, in figure 2.3b, a scatter plot of the data is presented, and it's apparent that the downward sloping linear model fit in red does not do a good job in describing the relationship between x and y. So again, let's look now at figure 2.3, now at B of figure 2.3, the right-hand side. Okay, and the downward sloping red line on the right-hand side does not do a great job in fitting this data. It's just apparent visually. Observe also that the confidence bands for this simple linear model may look deceptively appealing, tight gray bands around the red line, especially if one was only to look at these and not at the actual scatter plot of the data. The pitfall is that these confidence bands are computed under the assumption that the model fits the underlying process and data well, a case that doesn't hold here. Such a phenomenon is often loosely called model misspecification and is one of the risks that one undertakes and needs to mitigate when using statistical inference techniques. An alternative to the simple linear model is to seek a richer relationship, such as y equals beta 0 plus beta 1x plus beta 2x squared plus epsilon. One way of describing this relationship is via the function f theta defined for the d equal 3-dimensional theta via f theta of x is beta 0 plus beta 1x plus beta 2x squared, where x is still a scalar, that's p equals 1. An alternative description of the same model is to consider the squaring of the L-stat variable, that's x, as a new engineered feature, and thus now consider x as a p equal 2-dimensional vector, with x1 being the original feature and x2 being x1 squared, the new engineered feature. In this case, the model function is linear affine. F theta 0 of x1, x2 is as follows: beta 0 plus beta 1 x1 plus beta 2 x2. And the fact that x2 is a square of x1 is considered a feature engineering aspect and not a model function aspect. In practice, in this case, both approaches are identical and yield the same theta. Figure 2.3b presents the fit and corresponding error bands for this quadratic model in blue. So let's look at figure 2.3b one more time. So here is 2.3b. Okay, so that's this parabolic blue model, which seems more reasonable for this data. We mentioned that linear models for regression, which are the workhorse of classical statistics, can be extended in many ways. The notes at the end of this chapter point at some extensions, such as generalized linear models, that's GLM, mixed models, and more. Note also that nonlinear relationships in a regression context can be explored using smoothing techniques. Popular techniques in this framework are the generalized additive model, GAM, the locally estimated scatter plot smoothing, LOS method, as well as Nadaraya-Watson kernel regression. We also mentioned that generally when one considers feature engineering, one very important aspect is dealing with interaction terms. This means creating new engineered features that are based on the products of other features. The world of machine learning has adopted these models, often removing statistical assumptions, example about the noise epsilon, while introducing additional nonlinearities and mechanisms that yield very expressive models. The deep neural networks that we cover in this book include one such rich class of examples. We also mentioned that while the numerical house price context that we presented here appears to be simple and low-dimensional, regression problems can often involve extremely high-dimensional input feature vectors. For example, any regression problem where the input data is an image is of this nature. A concrete example of such a case using images of a human face is to predict the age of the person. Binary classification. Moving on from regression problems where y is continuous, we now consider binary classification where y attains one of two values, which are sometimes referred to as positive or negative. There are dozens of machine learning methods for binary classification, and our purpose here is not to explore how these methods work. Instead, we wish to illustrate how their performance is quantified. Our exposition relies on a logistic regression-based classifier, where positive samples are encoded via y equals 1, and negative samples are encoded via y equals 0. Note that in other scenarios, positive and negative samples are sometimes encoded via y equals positive 1 and y equals negative 1, respectively. Logistic regression is explored in depth in section 3.1 and 3.2 of chapter 3. For now, we can treat such a classifier as being based on a function f theta of x, where x is a feature vector. The output of f theta of x is a number in the continuous range 0, 1, indicating the probability that x matches a positive label. Hence, the higher the value of f theta of x, the more likely it is that the label associated with x is y equals 1. With the model f theta at hand, the classifier can be constructed via a decision rule based on a threshold tau, with a predicted output being, that's big Y hat, is 0. That means negative if Y hat, the probability, is less than tau, or 1 positive if Y hat is greater than tau, where Y hat is the output of the model f theta of x. So that's equation 2.5. In many cases, one selects the threshold at tau equals 0.5. However, as we see below, tau can often be adjusted. Also note the notational differences between y hat, that's a big Y, and y hat, just a little y. Throughout the book, we use the former to signify the actual predicted label for the classification, whereas we use the latter to denote the output of the model, which is usually continuous or numerical in nature. As an example, we consider breast cancer prediction where the label or outcome variable y has y equals 1 in case of malignant lumps and y equals 0 in case of benign lumps. A popular dataset in this context is called the Wisconsin Breast Cancer Dataset and is based on clinical data released in the early 1990s. Footnote 3 gives information about this dataset. We make further use of the dataset in section 3.1, that's in the next chapter, where we dive into logistic regression. The feature vector x is of dimension p equals 30 and is composed of continuous variables such as radius mean, texture mean, etc., each potentially affecting the probability of malignancy. The data has n equals 569 observations, and here we use the 80-20 splitting strategy, where we split it randomly between the training data and the testing data to have n train, which is 456, and that's about 0.8 times n training observations, and n test was 113, and that's about 0.2 times n testing observations. Note that in some of the sections below, we simply use n to denote n train when not considering the testing set explicitly. We may train different forms of logistic regression for this data, where we take x to be some subset or transformation of the original feature vector. At one extreme, we can take x to be a single variable, and at another extreme, x can be the full feature vector or even have additional engineered features similar to the home pricing example above. Here, for simplicity, we consider two logistic regression models. For the first model, we use only a single feature in X, which is smoothness worst, where the actual physical meaning of this variable is not critical for our understanding at this point. This model is denoted f theta p equals 1. So p equals 1 has a single feature. In the second model, we consider all 30 features in the data set. This model is denoted f theta p equals 30. For each of these models, we use the n-train observations to obtain an estimated parameter vector, where in the case of p equal 1, the estimated parameter theta hat is of dimension d equals 2. And in the case of p equals 30, the estimated parameter theta hat are of dimension d equals 31. So for logistic regression, the estimated parameters is the number of features plus 1. Similar as regression. Details on the actual meaning of the models and parameters of logistic regression are in chapter 3. With these models at hand, let's first fix tau and consider several performance measures of the classifier defined via 2.5. So again, 2.5 is a classifier that would take our, 2.5 would take our logistic regression model and then either get a negative or a positive depending on if we are less than tau or greater than tau. Okay. Standard way to compute a binary classification performance measure is to evaluate the classifier on the testing set. This then allows us to consider the predictions y hat y, that's a big Y, and compare them to the test set labels yi for I 1 to n test. Observations where big Y hat I equals yi are counted as either true positive or true negative, depending on the value of yi being 1 or 0 respectively. Okay, so that's true positive or true negative. Similarly, observations where this equality does not hold, as in here, are counted as either false positive or false negative, depending on if yi itself was, well, here, sorry, depending on if the prediction is negative or positive. These four counts, TP, TN, FP, and FN, total up to n test and are customarily summarized in the 2x2 confusion matrix. So here is the 2x2 confusion matrix. And in the 2x2 confusion matrix, we have the rows are in reality. So the first row are for observations that in reality in the test set are negative. The second row are positive. And the columns are for your decision. So a decision of a negative or a decision of a positive. And the sum of these four bins is the total number. In each one of them, we can actually put the count of the number of true negative, false positive, false negative, true positive. Observe the ratios at the margins of the matrix. So here we have some ratios of the margins. So we have this family of ratios, which are specificity and sensitivity. And we have this family of ratios, which are negative predictive value and precision. Okay. So these are the two different ways of looking at the margins here. Namely, sensitivity, also known as recall. So that's sensitivity known as recall. Specificity, precision, also known as positive predictive value, and negative predictive value. Okay. Now notice that in each one of these four ratios, we always have in the numerator a true. So true, no, negative, true, positive, true, negative. Okay. But in the denominator, we have the sum of the column where we're looking at. So true positive plus false positive for example, here. Okay, true positive plus false negative is here, etc., etc. Okay, so these are different ways of getting performance measures from this 2x2 confusion matrix. In general, we would like all of these ratios to be as close to 1 as possible. However, as we described below, there are often trade-offs. Now, an additional natural performance measure is the accuracy. It is simply defined as a proportion of correctly classified samples. Namely, accuracy is true positive plus true negative divided by the total number. So the accuracy is the diagonal of the confusion matrix divided by or the sum of the diagonal, the confusion matrix, divided by the total number of observations. This, namely accuracy, is often the first performance measure one considers. Yet for unbalanced data, it can be an extremely misleading measure. Indeed, a degenerate classifier that always predicts the most abundant class will have an accuracy equal to the proportion of that class. For example, in binary classification, if the positive class constitutes only 5% of the samples. Okay, so positive class 5% of the samples means that the reality, we only have here only 5% of the samples. Okay, that's that situation. Then the degenerate classifier, which always predicts y hat equals 0, will have an accuracy of 95%. Then even when considering some non-degenerate classifier, one observes an accuracy that is typically not worse than 95%. And if, for example, the accuracy is 99%, it is still not an indication that the classifier works well. A more robust analysis of performance considers the competing objectives of sensitivity and specificity. So we compare sensitivity and specificity. Okay, so comparing these two. Where a high sensitivity or recall value indicates a good ability of the classifier to detect positive samples, and the high specificity value indicates a good ability to detect negative samples. In the case of a threshold-based classifier, as we had in equation 2.5, varying tau alters the confusion matrix, and thus the sensitivity and specificity values are modified as well. A parametric curve based on tau, known as the receiver operating characteristic, ROC curve, is often used to visualize this trade-off between sensitivity and specificity, where so here's in this plot here, you have an ROC curve, where the x-axis plots 1 minus the specificity, also known as a false positive rate. So this is a false positive rate, 1 minus the specificity. Observe from the classifier at equation 2.5 and the formulas at the bottom of the margin of the confusion matrix that as tau goes to 0, the number of false positive vanishes, and hence sensitivity approaches 1. So as tau goes to 0, if we go back to 2.5, if you put tau as 0 in 2.5, so say tau is 0, so this thing is 0. Okay? If you had a 0 here, so you are always going to declare positive. Okay, so you're not going to have any false negatives because you always declare positives. So the number of false negatives vanishes, and hence sensitivity approaches 1. Because if you look at sensitivity, so look here at sensitivity, if you have 0 for the false negatives, then this goes to 1 because it's a ratio of true positive divided by true positives. Okay. Similarly, on the other end, if tau goes to 1, the number of false positives vanishes because you take everything as negative, so you don't have any false positive. You never declare positive falsely, and the specificity approaches 1. So then specificity, you're not going to have anything here, so this is 0, and specificity approaches 1, no matter what. Okay. More generally, as we vary tau between 0 and 1, a trade-off emerges is captured in the ROC curve. This allows us to tune the threshold tau for balancing sensitivity and specificity depending on the problem at hand. Figure 2.4 presents the smoothed ROC curve. So it's smooth because with a finite number of observations, we'll actually get jagged jumps. For the breast cancer example, where we compare the ROC curves for the p equals 1 case. So that's the p equals 1 case and the p equals 30 case models, as well as a coin flip. This is a flip. This is a random coin flip model, chance line, and the ideal. And this is the ideal. Receiver optimum characteristic curves allow us to assess the quality of models, taking all possible threshold parameters into account. A related measure that tries to quantify the quality of the curve into a single number is the area under the curve measure, and that's just the area under the curve. For a classifier with an ROC curve that achieves perfect sensitivity under any level of specificity, this measure is at 1 and corresponds to perfectly separable green curve in figure 2.4. So the area under here is 1. But for the less than ideal cases, the area would generally be less than 1. However, for classifiers that just choose a random class, this measure is at 0.5, corresponding to the chance line. That's this 45-degree vertical line. In the case of the breast cancer data, we see that on the testing set, the AUC for the p equals 1 model is 0.7, and for the p equals 30 model, it is 0.92. This may give an indication that the additional features in the richer model help obtain a better predictor. Let us now fix the threshold tau equals 0.5 and compare a few more performance measures. The test accuracy in this case is 0.73 for p equals 1 and 0.89 for p equals 30. However, since the number of positive samples in the test set is 40 out of 113, we see that this data set is somewhat unbalanced, and hence accuracy is not a good measure of performance. In such cases, machine learning practice has converged on a measure that averages precision and recall. Recall is also sensitivity. This could have alternatively been an average of specificity and sensitivity, recall. However, the common practice in machine learning has chosen precision and recall as the measures to use. Precision, similar to specificity, approaches 1 as a number of false positive approaches 0. However, precision is based on the true positive, while specificity is based on the true negative value. Okay, so however, precision and specificity. So compare here just, so what we're saying in machine learning, we use precision and recall. Okay, so we don't use, in machine learning world, we do not use specificity typically, but rather use recall, which is in statistics sometimes called a positive predictive value. Okay. You compare these two measures. For the p equals 1 model with tau equals 0.5, so let's now just stick the threshold 0.5. We have the precision true positive divided by true positive plus false positive is 0.7. And recall is 0.4. And for the p equals 30 model with tau equals 0.5, we have precision as 0.82 and recall is 0.9. So now we want to average these two and these two. A popular way to average precision and recall is by considering the harmonic mean of the two values. This is called the F1 score and is computed as follows. So the harmonic mean of two numbers is the inverse of the arithmetic mean of their inverses. So F1 is 2 divided by 1 over precision plus 1 over recall, which you can also represent like this. Okay. By multiplying numerator and denominator by precision and recall. In our example, for the p equals 1 model with tau equals 0.5, we have F1 equals 50.8%, and for the p equals 30 model with tau equals 0.5, we have F1 is 85.7%. Note that one may also use F1 scores to calibrate the threshold tau. Sometimes one uses a generalization of F1 called the F sub beta, where beta determines how much more important recall is in comparison to precision. However, in general, if there's not a clear reason to price false positives and false negatives differently, then using the F1 score as a single measure of performance is sensible. The bottom line is use F1 and not accuracy, and we see that F1 for the 30 feature model is at 85% versus or almost 86% versus about 51% for the F1 for the one feature case. In general, cases of unbalanced data should be treated with caution, not just in terms of performance measures and threshold calibration, but also in terms of inference. Further discussion of methods for unbalanced data are discussed in the sequel. Approaches and algorithms for supervised learning. We cannot cover all aspects of supervised learning in a single section, a single chapter, even in a single book. Yet now, after getting a taste of supervised learning in the context of regression and classification, let us discuss a few general approaches for supervised learning. Towards that end, we first distinguish between discriminative models and generative models. Most of the models in this book are discriminative. This means that when viewed through a probabilistic lens, even though we mostly do not do that, they're based on learning aspects of the distribution Py given x, i.e., the conditional distribution of the label y given the feature vector x. This is the case for linear models, logistic regression, general neural networks, and multiple additional models and algorithms not covered in this book. In contrast, generative models involve learning the joint distribution Pxy as a byproduct. Knowledge of Pxy also means knowing the marginal distribution P of x and P of y, as well as the conditional distributions Py given x and Px given y. Hence, generative models consider all of the data relationships as being learned, not just Py given x. In this book, the most prominent appearance of generative models in the context of generative adversarial network GANs appearing in Chapter 8, and other elementary generative models that we do not cover includes the famous naive-Bayes classifier, classically used for email spam detection applications, as well as linear discriminant analysis, LDA, used in many experimental statistical contexts. Naive-Bayes classifiers work by assuming that the distribution of a feature based on all other features in the label simply depends on the label and not on the other features. This naive independence assumption then allows to represent the likelihood function of the sample easily. This allows us to carry out generative learning inference efficiently. Further details are beyond our scope. LDA-based classifiers are also generative models, even though the name discriminant might be misleading. These classifiers fit a multivariate normal model to the data to carry out classification based on linear boundaries. Further details of both of these classifier models and algorithms are beyond our scope. Just a footnote, the likelihood function is a basic statistical concept that we survey in Chapter 3 in the context of logistic regression. In terms of discriminative models, the linear models, logistic regression models, and more general deep learning models in this book are very common examples. Linear models and logistic regression models are simple deep neural networks. Linear models are studied in detail in this chapter. Logistic regression models and generalizations are the focus of Chapter 3. General fully connected deep learning models are the focus of Chapter 5, and other specialized deep learning models are in Chapters 6 and 7. Beyond these deep learning models, other types of popular machine learning models that we do not cover in this book include support vector machines, decision trees, and their generalizations, which include random forests as well as gradient boosted trees. There are also additional elementary models often used for instruction of machine learning, such as the class of k-nearest neighbors classification models. Indeed, the world of machine learning is vast, with ideas and algorithms for creating both discriminative and generative models. The notes and references at the end of this chapter point at key resources. Okay, We hope that you found this section 2.2, which we just included, useful. Let us know what you think in the comments below. Thank you.